This is the Statics Zoom lecture, Tuesday, April 28th, 6 p.m. And we're going to cover deflection in beams tonight and Thursday. And then that'll leave us next week for column analysis. And then we'll do a final exam the week after, probably towards the end of the week. But we're working on the specifics there, and we'll give you all the information for that. Page 402 in the book gives a really good description, a really good discussion, if you will, about deflection in beams. And so we'll take this down here. And we will, so right in here, let's see, the design of beams for load and support conditions. We have investigated bending stresses and shear stresses, but now we're looking at something else that might govern the design, and that's permissible deflection. And the word deflection is really another word of deformation for beams, okay? And so deflection, which is a stiffness requirement, represents a change in the vertical position of the beam due to applied loads, load magnitude, beam span length, moments of inertia, modulus of elasticity. So we're starting to combine statics with strengths of materials. And there you have it, okay? Allowable deflection or permissible deflection. And we're going to show you a little bit on the a little bit about the codes, not a lot. You're going to get into this a lot with structural theory. Okay, so they talk about wood as a structural material, less stiff, lower E value, modulus of elasticity. You know, deflection is a concern, but it is also a concern with steel. And let me give you some examples. One of which would be Evans Tower. I always like to show this slide. This is from the mid-70s to maybe early 80s. This is the at that time. Hey guys, hey, in the background, let's watch the volume. Otherwise, I have to mute you. I really don't want to do that. This is the old entrance to the campus. It used to be a ball field. Don't get me talking about that too much, or I'll cry because I miss it. You know, you've got Smith Hall and the Wall Complex over here, so it's kind of a cool, cool picture. This is the building where Evans Tower used to be. That's Bush Hall, which had been constructed a couple of years back, and just some old pictures. That's a cool one right there. So just a little bit of history. But what they did is they started to. There's a neat truck. They started to analyze this in the early 2000s because they were getting some problems with the brick. And you can see the condition of the brick right here. And it dealt with what's known as a soft joint, which some of you saw in commercial construction. Some of you built the soft joint. And so here's a steel angle right here that is the support for the brick above the windows in E-Tower. Okay, there's also, you can barely see it right over here, and you can see the condition of these shelf angles. That's what they are. So we can have deflection along the length of the angle, right? The length of the angle, but you can also have deflection laterally, if you will. And you can see that that's quite an issue right there with the deflection of the angle outwards, if you will, outwards and down. I have some photos, I cannot find them unfortunately, of the deflection of Kinsella Hall, which is directly across from the library. And it's where the racquetball courts are. It's an overhang as you walk from the library towards Farrell, towards Kinsella. If you come right out of the library, keep going straight, and there's that overhang. And they had a tremendous amount of deflection in this, in their shelf angles as well. Hopefully someday I can find them. And there's another shot of the shelf angles also in fairly poor condition. This is the soffit right there. So they had to go through and fix all the brick that you can see bumping out. They had the expansion joints, the vertical expansion joints were in bad shape. Cost them about $250,000 to fix that. And you can see where the brick is bulging out. And a lot of that is because there was no soft joint, which is the brick that comes up underneath the shelf angle. You can't see it, or you can barely see it. See, that doesn't work. You can barely see the shelf angle in there. And with the brick underneath it, that should be an expandable material and caulking, not mortar. And so that's what was giving all of the problems, or a lot of the problems, with the with Evan Tower. And you can just see all the issues there. So they went through and they investigated this. They actually tore a hole right in the curtain wall. The brick is the curtain wall. They exposed the flashing. They exposed the structural steel. Okay. And then, let's see, we had some, let's see. And there was one more picture. Oh, I did have that, okay. Oh, so what they did is they started to take out the brick and put in better flashing, put in a soft joint. It was quite an involved, and there's the new flashing. And then here's a soft joint underneath it. So the flashing is sitting over that steel angle. So some big, very expensive issues with deflection. Okay. So let's see here. Allowable deflections, right? They're given in table 8.1. We're going to talk about those in a minute. Actually, we'll talk about them in about 2 seconds. And so this is just a little part of the code, recommended allowable deflection limits. And it basically is dependent on the use classification. Then if you're talking about live load or a combined dead and live load, and the L, the small L, is the length of the span in inches. Okay, so we're going to analyze that for the deck load trace that we did. Okay, and then you're going to see some. Let's go to something known, and you've seen it before. The golden rule now is for deflection. We had allowable stress design, which was the golden rule. Actual stress is less than allowable stress. And now the symbol for deflection is the triangle. So actual deflection has to be less than or equal to the allowable. And then there are common cases of beam loading, and that'll take us into the discussion about the deck load trace that we've been dealing with. Okay, so these are just, so you got your L, your W is your linear load, 384 is a $5 constant, E is modulus of elasticity, and I is moment of inertia. And it makes sense. The deflection is based on the length, the loading, and the modulus of elasticity and the moment of inertia. And here's some other sports. Here's the cantilever that we talked about. Okay, and we might get to that on Thursday night. That's with a uniform load. I don't think we did one of those yet. Yeah, we did this one. Actually, we might have done a combined of the two. So those are pages 402 to 407. And one other thing that, write that down. something that we won't get into, but you will with structural theory. On page 419 is lateral buckling in beams, okay, side to side, lateral buckling. So that's, that ties into a stability discussion back in chapter 4. So that's something, oh, and here's a, this is page 421, some lateral bracing requirements for timber beams, okay? But again, you know, diagonal bracing and so on. We just run out of time to get into that. But that's something that you'll definitely see in structural theory. So let's run a few calcs, and then we'll give you an easy homework that'll be due. Well, we'll discuss that at the end. You tell me what's working for your schedule. So let's look at this, and this is the right. This is the deck load trace, and we just keep adding on to this case study. So we've gone through the loading conditions. We got the reactions. Right. We got the shear moment diagrams, which gave us maximum shear, maximum moment. And then using those maximum shears and maximum moments, we calculated actual shear and bending stresses. And then we compared them to the allowable bending stresses, which was dependent on the type of wood that we were using. And so that's the allowable stress design, also known as the golden rule. Now, if we get into deflection calcs, and we're only going to deal with that interior deck joist. And again, the deflection symbol is the triangle. There's the pages that we talked about. Oh, stability, we just showed you a couple of pages out of chapter 8. And these are the pages out of chapter 4. And again, a lot more about that in structural theory. So the question is, can a beam fail without actually falling down, right? That brick shelf on Evanan Tower, that steel angle, actually was failing. You know, little bits of brick were falling off the building, but it was not a catastrophic failure. But it was failing in deflection. It was also failing in the stresses on the masonry itself because of the lack of a soft joint of the brick coming up underneath the steel angle. So let's look at another example. This is an oldie but a goodie. Can't believe I still have it. This is a pavilion down in the village of Delhi from back in 2005. So at that point, we went down and analyzed it, and it really doesn't look too bad from this angle. Till you take a look on the other side. And I would dare say that that was failing in deflection. So that's why I put a little holy shit. Hopefully we, oh yeah, we are recording that. That's okay, that's not too bad. But eventually what they did is they just tore the whole damn thing down and built a new one. Okay, again, we treat deflection very similar to stresses, the golden rule, allowable stress design analysis. We talked a little bit about the codes and how we calculate actual deflection, and basically another golden rule. So those pages that we talked about, 406 to 407, showed us those deflection formulas for common cases of beam loading. But our deck was not included in those pages. This really is our deck, right? This is the loading diagram of our deck, where you had R1 is the ledger, which is, structurally connected to the foundation wall. R2 was the main girder, which is supported by columns, which is eventually supported by Mother or Father Earth. So actually one of you in your homework was able to calculate the reactions using these formulas, okay? And in structural theory, you'll get into these formulas a lot more. So if you look at this, this is out of the code book. Can't remember which book I got it from, but again, delta X right here, these two formulas are blown up right here. So these are going to be the formulas that we're going to use to find the maximum deflection between the supports and the maximum deflection on the overhang. Okay. The shear diagram should look familiar. The moment diagram should look familiar. And then these are the maximum, they're the maximum deflections based on loading and where the supports are. And Mr. H made me promise I wouldn't make you use these formulas. So I wanted to, but he told me not to. He told me to knock it off. So that's a little joke. So that went over well. So we'll go back to the deck loading. That's most similar to our case from the text, makes it a little bit easy. So from the text, this is table 8.2. So I've grabbed this. This is a uniform load, simple span, and we're basically going to say, hey, let's analyze it right here. Okay, what's our maximum deflection going to be at mid-span between two supports, and again in the middle of the span. So that's our maximum deflection, and there's our 5 WL to the fourth over 384 EI. So that's actual deflection. What about allowed deflection? Well, let's go to table 8.1, page 403, which we just were talking about. And again, the L is the total span between supports. The larger the number in the denominator, the smaller allowable deflection you're dealing with. And if you think about it, those steel angles that support the, where the hell is it? That support the brick in Evenden, those are going to have a certain allowable deflection. That's probably going to govern. Okay. So that's a good example. So we're going to go to here. And so here's our deflection calcs. So again, what we want you to do is we want you to calculate the moment of inertia, the maximum deflection, which is going to be this formula, and the allowable, which is based on this table right here.
So the formula for deflection max is basically for the deflection actual, right? For the actual deflection.
Yes. Well, when you see our results from the lab, we'll talk about it a little bit today. My actual deflections based on a certain loading weren't that great, but our equipment is old. But yes, the formulas that you're going to use, the maximum one for a simple span, we're assuming that ours is a simple span, it's going to happen mid-span. And that's going to be the formula for it.
So where did the 384 come from?
That's a $5 word for a constant. So some research engineer smarter than me came up with that one.
So that's a constant?
Yep.
All right.
Yep. And so is the 5. But the one thing you got to watch out for is if you take a look at this, the units of E, what are the units of modulus?
Roll tighter down on the list, Jay Sean, check out what
It's inches.
What's the units of modulus of elasticity?
Inches?
Nope. Actually, I don't know. Has the unit quiz been posted yet? The next unit quiz will.
Ronaldo, help us out.
That'll be posted probably tomorrow. So you'll have a day or two to do that. And that may be on the quiz. So this is, E is pounds per square inch. And so you have pounds and inches. So the I is moment of inertia. That's inches to the fourth, right? W is typically in pounds per foot. And L is in feet. So you got to watch your units. Otherwise, you'll get your maximum deflection is going to be way off. So right here, there's your formula for moment of inertia, BH cubed over 12. What was the size of the deck joist? That was a 2x10. So the base is 1.5 inches. The height is 9 1/4. Cube the height, divide that beast by 12, and that's your moment of inertia. So you got to show me the calcs for that. And then there's the formula, 5WL to the fourth over 384 EI. So you've got to set up the formula right here and show all of your conversion factors. Okay, I want to see all the conversion factors using dimensional analysis. And then the allowable, we're going to say that it's going to be L, which is the span between supports. Let's get that. Okay, the span between supports. So you got to go back into the deck problem. And what was this span right here? You're going to use that span. So that span divided by 240 is going to be your allowable deflection. Now, the L, the span, has to be in what units? It'd be in,
Feet.
well, it's given in feet on the free body diagram, but deflection is always measured in what units? Units of length, but what units in the English units do we use?
Inches.
Hell, don't want to list your deflections in feet. If you've got deflections that are feet, you got a problem. So that's what you're going to see on the final stuff like that. Tons of units, and actually we're getting pretty close. It's just this week and next. And then you're going to say, did it pass or fail? Was the maximum based on the loading and the type of material, the size of the material, did it meet the golden rule, which is the pass fail? Okay. I'm going to turn my pacemaker off. Okay, so that's due, what's tonight? Tuesday. Our next Zoom is Friday, correct? So let's make this due Thursday night at 11:59. How's that sound?
Sure.
So that is 4:30 at 11:59. Easy 20 points. And again, we'll post this lecture to Vanco. And I still got to grade tomorrow. I got to grade the ground freezing. So I haven't graded those yet. I think that's the only one that I need to grade. Oh, no, I got one more. I've got the old load trace cone of silence from the last lab that we met in person. So I got to start picking away at those and get those done. Okay, so that's where we're at there. And one thing we're going to talk about on Friday is a deflection lab. So we're going to, and this is the rig that we set up in in Lab 18. Very basic. This is actually a yardstick, and this is a wide flange beam, and then we're deflecting this 2x4. So we know that the 2x4 is going to deflect before that beam deflects. Now I'm going to show you a couple of videos of what I'd like to, what I wish I had for, you always got to watch out for YouTube. Make sure you don't put some shit on there. So this is a really cool, I think I've shown you pictures, but I've never shown you a video. Now that is a universal testing machine. That's the one where they can break a column about 35 feet tall. So they've done a concrete beam. Sweet, huh? So, is that and you can't hear my volume, can you, on the YouTube?
No.
Okay.
No.
They taught me how to do that, and I didn't make a copy of it. But there's a couple more shots of it. But that shows a great, and then here's another one. This is a little bit bigger than what we're able to do. Now see if you can hear the tell you what, let me just check something here. I actually got to tour this on my sabbatical. Can you hear the sound?
Yes.
No, that's destruction. So here's a cool, this is quite the beam. You start seeing the cracking. Now you can start to see the deflection. Sweet. And this should look familiar with my lab. Let's show that again. One of you did a nice job with the slow-mo. And I got my first loved it comment. So I got that going for me, which is nice. So we will talk more about that. And so let's see, we've got to do a new share. No more of that. Share the screen. And go back to here. Did that. So we'll start this. We'll play around with this on Friday. And here's the YouTubes that I just showed you. This one is due Thursday night. This one will be due over the weekend. I'll put a Dropbox for this one tonight so that you have it. And then come up with any questions that you may have on this. Take a peek at this. You do have the Excel. This is a screenshot from the Excel. And we'll show you these where now we actually had a measured deflection. We had the maximum deflection based on what it should be theoretically. Okay. And then we dealt with our allowable. So now we said L over 120. We only used a 2x4. So we'll play around with that. So that's about all I have for you tonight. Let me just check my, yeah, that's about it for tonight. Again,
Can you repeat the page for the homework that's due on Thursday?
it's all on Vanco.
All right.
And, but it's basically on Vanco. Let's see here. If you go all the way down to the bottom, here's the updated. There's the deck load trace. This has been updated for deflection, so that's all 9 pages. There's the deflection lab handout. That won't be due till the weekend. And then this actually is for you folks for structural theory. Actually, I'm glad you brought up that question. The sculpture in front of Smith Hall is a gift, if you will, from industry. It's out of here. Should be a picture. Okay, we're going to go to this real quick. So there's the sculpture in front of, that's one of the students from back in the day. And that's the foundation for it. The heavy civil students built that, poured it monolithically, so we actually poured the column footing with the column pier all at the same time. That's what it looked like before backfill. Just one big old chunk of concrete. I remember it well because one of the students had a lot of money left over in his meal card, and we ate like kings every lab. God, that kid brought a lot of food. Whoa. Hint. And then we had, there's Mr. Vogt. And then they brought it in with a little lull and set it in place. So the beauty of it is that there are just many, moment connections, shear connections, you name it. And that's what this is. It's a teaching guide. So if any of you get into really high-end structures, and some of you do, this is a great 85-page report for you put out by AISC, American Institute of Steel Construction. Simple shear connections, bolted connections, and so on. So that's for your viewing pleasure. And that is within that week on Vanco Hall. So by tonight, there'll be a Dropbox for the deck load deflection. We'll talk about the deflection lab on Friday, and then we'll do some introductory stuff on column analysis on Friday and then all of next week. So that's the end of this
Mr. Keegan,
Zoom. Yeah, question.
do you know by any chance when our final would be?
Haven't decided yet. We'll probably do the same, maybe 3 or 4 hour block. You get 2 hours to do it. You may get a little longer. Depends on how long we make the final. It's worth 15% of your grade, so it's a biggie. And like I said, keep an eye open for units quiz for this week.
Okay. Thank you.
Any other questions? You're welcome. Okay, so that's the end of Zoom for Tuesday night, April 28th. We're going to stop the recording. Hope all is well for you and your families, and